I have a question. So you've been using this pair class. Here we have the simplest possible version of it. And now I have the person and student class that we've already seen. And now I have just some method that does something that takes a pair of person. And it takes a pair of person and somehow makes them friends. Yeah.
Press OK twice.
Yes. Which one is okay? Menu. So P is, the parameter has to be a pair of person. Or does it? So can you pass it only a pair of person? Or could you also pass it a pair of student? Because after all, a student is a person, so a pair of students, surely a pair of people. Can you pass it a pair of any? Or could you pass it pairs with other stuff in it, like pair of laptop? What do you think? Okay, this is going great. Everyone said unanimously, well, surely you should be able to pass it a pair of person and a pair of student. Okay, thank you for your cooperation. That is exactly the wrong answer that I was hoping that everyone was intuitively going to have. Yes, and so to explain why that is not the right answer and what to do to make it the right answer, that's the purpose of this entire module. So the correct answer is, in fact, A. Because by default, a generic type is what's called invariant. So if you have, in our case, pair of person and pair of student, there's no relationship between the two whatsoever. Neither of them can be converted to another, no matter what goes inside the brackets. So even though there is a relationship between student and person, there's no relationship between the pairs. Yes?
But if it wasn't generic, like a method that takes two persons.
Then if it just took people, like if it was make friends of P1 colon person, comma P2 colon person, then the subtyping relationship would take care of it.
Okay,
Right?
starts in generic.
But when you have it inside a generic type, then by default, it just doesn't want to do anything. And that doesn't sound totally intuitive, right? You would think, well, a pair of students is, of course, a pair of person. And why doesn't it work? So we'll see in a minute why it doesn't work in general, but I'll first show you how to make it work. And that's very simple. What you do is you add this little plus sign here. And that means that you want pair to be covariant in T. They're classes with more than one type parameter, and they don't have to be covariant in all parameters. But if you say, I want it to be covariant in T, which happens to be the only parameter here, then it is now out of a sudden true that a pair of student is a subtype of a pair of person. So you have to explicitly declare that that's what your wish is by putting in that little plus sign there. And in general, this covariance is a good choice for immutable collections. So for example, sequence. The immutable sequence is declared to be covariant in its type parameter. If you look into the Scala doc, here you see the immutable sequence, and up here you see a plus A, which means that it has exactly that behavior. If you have a sequence of students, that's a subtype of sequence of person. Anyone who processes a sequence of person will surely be able to take a sequence of students. And so by putting the plus here, we get the same behavior for the pair. Now, that does raise the issue, when you're going to put a plus, can you also put a minus? And so let's see where this would make sense. So here I have a trait. And this is a friend of T's. So someone could be a friend of people, a friend of students, a friend of cats. And so there's one method. Someone is a friend of T if he is willing to befriend someone of type T. So when you have a friend of cats, that person would be willing to befriend someone who's a cat. If someone is a friend of students, then that person only wants to be friends with other students, but a friend of person would be willing to be friends with any person. So now I have a function here that I call make friends with. So it takes a student, and it takes someone who is a friend of students. And now my question is in the second parameter. Surely I can pass someone who is a friend of students. Could I also pass a friend of person? Should I also be able to pass in a friend of graduate student? It probably doesn't make so much sense, but maybe you disagree with me. Maybe one should be able to pass a friend of anything. Maybe a friend of cats should be okay. So what do you think? Okay, so I'm not asking what actually works, but what should work. Okay, so in this case, I don't want to know what actually works, but I want to know if the world was a just place, what should one reasonably be able to get to work? Okay, can we get everyone to commit themselves to something? All right, so we have an interesting mixture of A's, B's, and C's after I've talked down a D. So now some of you said it should not be possible to put in a friend of person. So like you guys said A is the right choice. So why wouldn't a friend of person work? But if this was a just world, it should work, I think, shouldn't it? Because a friend of person, I am a friend of person. I'm willing to befriend any person whatsoever. You should be able to pass me to this method because it'll work, right? I will be befriending the student and all will be well. So there's no particular reason to outlaw a friend of person. It'll work. How about a friend of graduate student? There were a few people who said a friend of graduate student should be okay. So let's imagine someone what is a friend of graduate student? I'm going to randomly pick on someone. Like on the two ladies in the back row. They will only want to befriend graduate students. Regular students, not so good, but graduate students is okay. So should it be okay to pass them into here? Let's see what happens. So they would befriend an S. But that's not so good. An S could be any old student. So that should not work. So notice that now the type relationship has been inverted. That a friend of student is expected, but in this case it's actually okay to pass a friend of something more general. And it's not okay to pass a friend of something more specific. Whereas in the situation with the pairs, it was okay to form a pair of something more specific, but not a pair of something more general. So this is what's called a contravariant type relationship. And it's written by putting a minus in here. Oops. So the minus says that when we design the straight friend, then it would be most usable if we make it contravariant, if we allow it to vary in this way. Once we do that, then we say that when a friend of student is expected, it's okay to give it a friend of person. Another example, yeah.
Yeah, but in the question slide there wasn't a minus, so is it still B?
There is no, okay, the question that I want to ask is how should it be, right? And so you're totally right that that the way it is, of course, only this one works because types are invariant, right, by default. But So the question that I was trying to ask, and maybe I didn't ask it very well, is to say, what should one be able to do? So it's a design question, right? It's a question of how should one design these types. So the point that I want to make is sometimes it's very reasonable for types to vary, for the generic types to vary in the same direction as the type parameter. Sometimes it's reasonable for them to vary in the opposite direction. Both of those phenomena are legitimate. Both of them can happen. For collections, it's generally, it makes sense to vary in the same direction. For these kinds of things that consume things, it generally makes sense to vary in the opposite direction. Yeah?
So minus is for less specific and plus is for more specific?
I wouldn't say that. Plus means it varies in the same direction. If S is a subtype of T, then G of S is a subtype of G of T. And the minus means it varies in the opposite direction. And I don't actually know where the plus and minus come from. Why they didn't use like a less than or greater than or some such thing, but that's what they use. And it's not just in Scala, but there are other languages that do the same thing. So that means you have, for any given type parameter, you have three options. You can choose to make it covariant, you can choose to make it contravariant, or you can choose to make it invariant. So in the standard type function 1, a function 1 is a type for a function that takes one parameter and has one return value. You've seen this type written as T arrow R. That's just a prettier form for saying function 1 of T and R. The way function 1 has been defined is that T is contravariant and R, the result type, is covariant. That makes sense because suppose that you have some piece of code that that processes something, and as a function, it has something that wants students and that produces person. Okay, actually, I just used this example. I'm sorry. So we'll just look at this example here. So here we have a function that wants students, produces people, and can we call it with a function that consumes people and produces students? And the answer is sure, because somewhere in this friends operation here, it's going to call find. It's going to give it students. Well, it's willing to take any person, so surely it's willing to accept students. And it produces students. We only want a person, but that's fine. So you can always go into the minus direction on consumers, and you can always go in the plus direction on producers. So generally, consumers are contravariant and producers are covariant. And that's the rule of thumb that you want to keep in mind. What about, why isn't this always the case? Why aren't always collections covariant? I mean, don't they produce stuff? But it's not that simple. So look at an array class. And like we have in Java. And let's see if array could actually be covariant. So if we had an array of students, could we make it into an array of person? So could we pass an array of students to something that expects to get an array of person? Now, you would think what someone reads through an array of person, and if all they find in it is students, what's the harm? They're only expecting people. But the problem is, that's the reading part. What if you have stores? So look at this code here. So we have students is an array made out of these two students. Now we convert it to people, which is an array of, oops, I forgot to say that. And now look at the third line where it says people 0 is new person Fred. Will it compile? Well, sure it'll compile because the type of people is array of person, and it is perfectly legal to store a person into an array of people, into an array of person. And so that'll compile. The problem is that students and people are the same array because you have reference semantics, so you have students, you have people, They both point to the same array. Over here we have some student, and over here now we put in Fred. From the people point of view, that's not a problem. But from the student's point of view, it is a problem. Now we have an array of students that contains a non-student, and so that broke the type system. What happens when you do this in Java? In Java, it's perfectly legal to take an array of students and turn it into an array of people. But when you then do this store at runtime, you get an error. You get an array store exception. It doesn't happen. Did any of you ever have an array store exception? Like ever in your life? It's not a very common exception, actually. So the designers of Java said, we're going to build an unsound conversion and check it at runtime, because in practice it doesn't happen very often. And so that was a pragmatic decision that they made. Now, did they keep that pragmatic decision for other collections when you use an array list? No. Array lists in Java are invariant, so they did not keep that. And in Scala, arrays are also invariant, because Scala feels more strongly than Java that any type error should be found at compile time, that it should not be possible for a program to die with a type error at runtime. So in Java, one isn't quite so picky, but that's how it is in Scala. And so for that reason, it is simply impossible to define mutable collections that are covariant. It would be unsound. You can't have a collection that has both loads and stores and that has type variance in either direction. So having both loads and stores forces your collection to be invariant. Yeah?
I'm still a bit confused. Can I ask a question on the Blackboard?
Yeah, totally. Oh, hang on, I'll give you chalk. No, you can draw on this, then actually we'll get to record it. Here, take the pen and write on here.
So, if we have if we take minus b, would it be like this part or this part?
Okay, that's not really how it works.
Yeah.
Okay, so because really what you can't take minus off a concrete type. You can take plus or minus of a type parameter. So if you have a generic type and you say g minus t, now when we look at what happens when we map this thing under g, where we now have g of a, g of b, g of c. And when you have a minus, that means that the arrows flip. Whereas when you have a plus, then the arrows would go the same way.
So if we have g of b, we can, and like it's g minus t, and we give it a b, we can have.
So we want minus. Let me take the plus away, as not to be confusing.
What type does the function accept?
So let's now say we have a function that takes a g of b, right? So some parameter x of type g of b. Now, in this case here, it is also willing to take a g of a. And that's the case when the x is something that consumes stuff, like the befriending thing or a comparator. When it's willing to consume things of type B, then it's also willing to consume things of type A. Okay? So, in Scala, mutable collections cannot be covariant, but how can Scala tell what's a mutable collection? Does the Scala compiler look at the code that you're doing and say, hey, that person is collecting elements, so I'll make sure that it's immutable? I mean, there's no outward notion of what it means to collect elements. You know, what if you collect them in a database or something? And that's not actually what it does. It does something much simpler. So when it looks to see whether to allow or to disallow a certain method, it looks at the positions of the type parameters. So it looks at any old method and sees whether the type parameters occur in what's called covariant or contravariant positions. So let's look at a simple example. Let's suppose I design a pair class, and I will say I want it to be covariant, but then I make first and second as vars. So now it's a mutable pair. Then I'm going to get an error message that says, well, by declaring this var, you have actually declared two methods for first, namely the getter first, which yields a t, and you've also defined a setter that's called first underscore equals that's how it's called, and it has a t as an input. And then it's going to say this position here, this parameter here, has t occurring in a so-called contravariant position. And so the rule is very simple. A parameter of a method is in contravariant position. The return value, or the return type, is covariant. And it's going to check. This one here was covariant. That was fine for plus t. This one here was contravariant, not fine, and it'll refuse to compile it. That's a simple rule that actually is surprisingly effective, that allows the compiler to do the right thing, to disallow stores, because a store means something has to go in, it has to go in as a parameter, and to allow reads, and thereby distinguish immutable from an immutable collection. There's a little bit of subtlety, and that is when you have these positions inside function parameters, they flip. So I've given an example here, fold left. So let's apply the rule here. This thing here is a parameter, so it's in contravariant position. This thing here is another parameter, so it's also in contravariant position. But inside it, it has another parameter type, and because it's a parameter inside a parameter, it flips to plus. That's how the calculus goes, and this one here flips to minus. It turns out that that does the right thing, and when you stare at it long enough, you will convince yourself of that. And so in this kind of situation, the compiler looks at it and says, okay, let's see. B has a minus here, and it has a plus there. And so if B is not invariant, you're going to get a compiler error. So if B was annotated as either plus or minus, it's going to conflict one of these two positions. A, on the other hand, is only constrained by this plus here, so A could either be invariant or covariant. You'll see an example in the lab, exactly where this comes from, and then you can think about it a little bit and make sense. So that's the simple rule that the compiler uses to, to double check whether your pluses and minuses are used consistently. It just looks at the positions of these methods. And it almost always does the right thing, but there's a couple of situations when you have to help it out. So let's look at our friend replace first. So here I wanted to have a new pair where I replaced the first element. You've had that in the previous lab. And when I write this code, it's not going to work because the compiler goes through it. It's going to say, all right, t is a covariant parameter. Let's check it out. Here we have a bunch of vals. They give rise to methods, these invisible getter methods. Those are fine because they return something that's a covariant. Over here, we have, we have a contravariant t, and it's not going to compile it. Even though it would be perfectly safe because we're not mutating the pair. We're returning a new pair that contains that other element. So the compiler is not smart. It has no idea what the difference is between mutation and making a new thing. It simply says, because of the positioning, I will disallow this. But there is a simple remedy that's slightly laborious, and you've seen that remedy. It's exactly what we've done before. So you put a new type parameter in here. You say any supertype of t is fine. That's the parameter of the thing that's in new first, and then we just make this new pair. It's actually more descriptive, because here now we get the new pair properly typed, whereas over here we lamely said it has to have type t. So what you have to remember is, if you do design a generic type, and maybe that you never have to design one, but if you do, then it's actually, when I do this, it's somewhat common. I first make this mistake, and then I realize, oh, I need to do this remedy. Another thing where you have to be a little bit careful as a user of this is objects can't be generic, because an object means it's a singleton, and there's only one. There's not one per type. One could imagine a world where there would be one per type, but in the Java virtual machine that doesn't easily work. And so you run into this with empty objects. So let's say I want to make a generic list class. So I want a covariant T because it's a read-only list. I have my case class colon colon that has a head of type T and a tail of type list T, well, like what you've seen in the lab last week, now except with the generic types. I have a case object for the empty list. I only want an object. I don't want to have a whole class because there's only one. But I can't put angle bracket T behind here because of the special rules. Objects can't be generic. But I still want it to be a list. See, I still want inheritance to work out, so I want the extends list of T here, and so I have to write extends list. I can't just write extends list because it's a generic type. I have to put an A type parameter. And this is where that magic type nothing comes in. I say it's a list on nothing. And this works fine because list of nothing is a subtype of all list of T because list is covariant. So nothing is a subtype of T, so therefore list of nothing is a subtype of list of T. So as an example here, let's analyze in gory detail what this call here means. So this wants to make a new con cell out of 42 and nil. And so the question is, can it really pass nil into this constructor? Well, clearly T is inferred to be int. So the head needs to be an int, which it is, and the tail here needs to be a list of int. Is it a list of int? Well, it's a list of nothing, and that's a list of int. Now, I can't say that I find this particularly intuitive. Why would a list of nothing be a list of int? But if you follow the rules, just the calculus, it's true, right? Nothing is a subtype of all types. That's the definition of nothing. It's covariant, so this must be true, and therefore you can pass it. It kind of helps out that that is not actually a nothing, and so you don't actually have to ever think about what this means. It just works out formally. So that's that's where the nothing comes in. So let's compare this with Java. So in Java, you've probably never seen these pluses and minuses, and there's a good reason why you haven't seen them, namely they don't exist in Java. This was considered. The designers of Java were perfectly aware of how to do this, and there was an early prototype of it written, if I'm not mistaken, by Professor Odersky, the creator of Scala, that did in fact use the plus and minuses in exactly the same way, but they weren't happy with it. For one thing, collections in Java were always mutable. That's just how, in the spirit of Java, and so there the variants didn't buy you a lot because you couldn't you couldn't declare collections in any way. And the kind of things where in Scala we have a lot of covariants and contravariants are these functional constructs. They didn't exist in Java until very recently. They certainly didn't exist 15 years ago. And so the fact that maybe it would make a lot of sense to have consumers to be contravariant just didn't solve a problem that people had. But the problem that Java had in spades was that you had these invariant collections, and you still wanted to write generic functions that worked on them. So for example, consider copy. So this is something that I've taken out of Java util.collections. There's a static method called copy that copies one list into another. Well, how do you write it in a generic way? You could write it so that it can copy a list of type T into a list of type T, but then what if you want to copy a list of students into a list of person? That should be possible. And so the solution in Java is what's called use site variants, that you define at the site where you define the function, not at the not where you define the class, you define how the stuff should vary. And so the syntax in Java is a little bit funny. You use these wildcards. So here we have a list of some supertype of T, and that's the destination, and some subtype of T, and that's the source. So you could put a list of graduate students into a list of people. So T would be students in this case, and that would work fine. Why does it say question mark super T, and here it says question mark extends T, and it's not question mark sub T? So why doesn't it say, oops, why doesn't it say sub here? Why does it say extends? Oh, because this stuff was added in Java, what was it, 1.5? And as it happens, super, by fortuitous circumstance, was already a keyword in the language. But sub was not a keyword in the language, and they weren't about to add one. In fact, I was there when the syntax was invented. Someone gave a presentation on this stuff, and there wasn't super yet. They only used extends, and then they had it written in the other direction, T extends question mark. And someone in the audience said, hey, you could use super for that. And that's how it was born. So that's always what happens. They also tried the version with the less than equal or greater, less than colon and greater colon like we have in Scala. And when they field tested it with programmers, remember Java is what's called a blue-collar programming language, a language for people from all walks of life, not just academic types. The heads exploded, literally exploded, when they saw the less colon and colon greater. And so they said that they couldn't do that. But still, when you show the stuff to people, then their heads still explode. So most people do not like this very much. It gets particularly bad when you deal with comparators. So here is, and I'm not making this up, here is the prototype for the sort function. So sort takes a list of t's, and then it takes a comparator of something that is question mark super t, because if you have, say, a list of students, and now you have a comparator that is willing to compare arbitrary people, that needs to be okay. And so that's the syntax that they use. You can do the same thing in Scala. In Scala, the syntax looks almost the same, except you use the wildcard symbol for the question mark, and you use the more mathematical supertype and subtype symbols. Yeah?
What is the difference between underscore greater than t and plus t?
Oh, there's a huge difference. The plus t is a declaration site variance. That means for the entire class, you want it to vary in that way. This one here means for this individual method, you want to vary it like this. And so the declaration site variance is useful if it always has to be true. Like for a covariant collection, for a mutable collection, it always has to be like that. The use site variance is one when you can't make a general statement, but for any individual function or for some individual functions, you want to set the rules. And for many years, Java was actually well served by this use case variant because that happens a lot. That you have something that generically you cannot make any assertion about variance, but when you have a particular method in mind, then you can. Where it's breaking down now is with lambdas, that one generally wants these function expressions to be contravariant, and you can't do it. And in every single use, you have to put question mark super t. If I got the dollar for every time that I typed question mark super t in the Java 8 book that I wrote, then I would double my royalties. So, so now in Java, they kind of regret that they didn't go the route that Scala did, where Scala gives you both. So Scala very sensibly says declaration side is very nice when you can make that general assertion, but when you can't, having the use side variance is nice too. All right, so this is variance, and so this is really something that is at the heart of having a type system that has generics. It's very difficult to build a useful type system with generics that does not also address variance. Everyone who has tried has not been successful with that. So when you have I should say, if you have a language that has inheritance, if you have inheritance and generic types, you really must address variance, or you're going to build something that people will not enjoy using. And and Java does the use site variance, which is good enough for its use. Scala is making a much better effort in giving you both. But the devil is in the details, as you will see in the lab. It starts out pretty simple. That you'll see that the rules are actually they're reasonable, they, even some of the things that are at first glance unintuitive have a good reason. And when you design things, it's usually relatively easy to figure out what should be covariant, what should be contravariant. So I'll give you some examples of, like a map. And, think about it. If you have a map of KV, what should K be? Should it be plus or minus? Should V be plus or minus? And there is a correct answer to this, a reasonable and rational answer that you will find in this lab. And then it goes downhill. Namely, when you interact with actual real types that are out there, particularly the comparator and ordered, where you have to deal with mistakes of the past. And that's what makes variance often unpleasant and unreliable for people to use. So just as before I let you get into the lab, this whole issue with variance has shell-shocked programming language designers. That it just is more difficult than it should be to get this kind of stuff right. Joe Programmer does not understand variance and is often baffled by why things are outlawed that in their mind should work just fine. And it makes it difficult for them to, for average programmers to write correct code that uses generics. So what people have now tried is to build type systems that are a little bit more forgiving, that let you write stuff that the arrays are like in Java, where, yes, it's unsound, but as long as you make these mistakes only rarely, maybe that's a reasonable trade-off. So when you look at a language like Dart, for example, so in Dart where typing is optional, they do this on purpose. They say, okay, we're going to make these decisions that are unsound. We're going to allow programmers to make these decisions in their generic classes, and thereby it greatly simplifies the load on what the average programmer has to do. No one knows whether that's the right direction to go. Scala has taken the approach, and it is certainly a very principled approach that says types are important, types should always be right. And as you'll see in the lab, to follow through with that does mean that sometimes you have to do a fair amount of work that at the outset seems surprising. So let's do this one. So this lab here I think is super useful, and so I really want everyone to totally focus on this one. All right, and I'll go around and see what questions you guys have.